Okay.
Hi, I'm David Christensen.
And I'm Doug Graff.
Our project is on drone delivery, specifically path planning in an urban environment. For the overall scope of our project, the idea that we had was to have a team of vehicles and cars going through a city like New York and planning the best routes to deliver packages. We scaled this down, as you'll see in our next slide.
Yeah, so our project is split into two pieces. We've got the 3D path planning portion and the traveling salesman. So a continuous part and a discrete part. David handled the continuous part. I handled the discrete part.
Yeah. So to talk a little bit about the path planning portion, the 3D path planning, there's a variety of ways to do this. We chose to do this using RRT. So RRT is a method that it stands for rapidly exploring random tree. And what it does is it creates a random point in space, starting out with a initial node or point. Um, and it looks for the closest point in space and makes a connection with it. However, if the connection intersects an obstacle, then it doesn't make that connection and it creates a new point. And it does this until we have these many paths throughout space. And then it ends up choosing the minimum path from the end point to the starting point. A variant of this, as you can see, one trouble with RRT is that it produces these cubic paths that aren't very smooth. So RRT star is an improvement in this, and it's basically the same algorithm. However, it creates with it, it chooses a radius, and instead of choosing the closest point to the randomly generated node, it chooses the node within a radius that has the minimum path to the starting point. And then also within that radius, any node that would have a shorter path by connecting to it is also connected to it, rewired. It takes much longer, but it produces these better looking graphs. Here's going back, sorry. So in order to do this in 3D, we had to come up with a way to do obstacle avoidance. And I did this doing 3D ray tracing. So using 3 points in space, we can come up with the equation of a plane, and it makes a triangle. And then also using these 3 equations for the equation of a line parameterized by t, we can figure out if this line segment intersects this triangle. First, and then extending this to an obstacle, we can create basically any shape with these triangles. In our case, we just chose to do a rectangular prism. We can see if it intersects. This is important because in this case, as shown in the image, we get intersections of an obstacle if it goes all the way through and if it's inside of the obstacle. Whereas if we just checked a single point, if a single point was in a space, we wouldn't get this complete intersection. So here's an example of RRT in 3 dimensions. As you can see, it produces a relatively good path, but the shape is not very smooth. This is in 600 seconds, and it produced 3,000 points about. RRT star produced a somewhat better path. However, it was much slower. It only produced 434 points. So in order to do this in the scenario that we created, in our case, we want to get a path from each node or destination. Each red dot is a destination where we want to take a package to. So we want to produce a path from each point to every other point and then feed this into the traveling salesman problem. However, in order to do this with RRT, it would have taken an extremely long time to perform the RRT algorithm from each node to every other node. So instead, I created these initialized points, which if you think about having a map of a city, we could basically create this initialized graph with points along the road and then points up in space to the height of the building. So this was just to ensure that there is a path to every other node when we run the RRT algorithm, and that we only have to run the RRT algorithm once, and using the network that it creates, find the best path from each node to every other node. We add the RRT star part to it afterwards by optimizing the best path and removing unnecessary nodes in the path created. So this is the results. So in this case, I ran the algorithm for about an hour. As you can see, an aerial view is also a side view of the generated paths. Of course, if I ran this longer, it would have produced better paths, but these are relatively good. The star runtime, or optimizing the paths afterwards, removing unnecessary nodes, took about 9 minutes. And then the number of points generated was about 5,495. So in order to go through these paths with the quad rotor, it's possible to just go to these waypoints that we generated in 3D space. However, to get better performance and also to reduce the time, it's better to have a trajectory that the quad rotor could go through. I worked on this by producing Bezier curves in MATLAB, and I chose to do a third order Bezier curves, and their Bezier curves are defined by these control points, those red dots on the left, and those characterize the shape of the path. In order to produce like a full path, we have to do a composite spline of these Bezier curves, where in between each two waypoints, you have a curve. And we can turn this into an optimization problem. As you can see on this next slide, we have these constraints at the top. We're trying to minimize the time. So the design variables are the time at each node or waypoint, and these control points, the points in space that those green control points are at. So by changing those variables and minimizing the time between the end node and the start node, we can produce this spline subject to these constraints which ensure connectivity, smoothness, and feasibility. However, the velocity constraint was much more difficult than I thought it would be to produce, at least through the whole line. The reason for this is because the graph, the polynomial describing the magnitude of the velocity is quadratic, because we have each segment, the derivative of each segment defining the velocity, but we have to square that to get the total velocity in each direction. So I just constrained the velocity at each waypoint. However, we didn't get this this parameterization into the full optimization for the paths, but this is just showing what we would have done if we integrated this into all the paths.
So for the traveling salesman portion, I chose to use simulated annealing. You can use other algorithms like the genetic algorithm or something like that. But we did just talk about this, so I'll be really brief. You basically just swap the order of the nodes that you get, since it's a discrete optimization. So you're going to swap the nodes of the order, or yeah, swap the order of the nodes, and then you decide whether that benefits you or doesn't. And if it benefits you, whether it's a better solution or better criteria or meets the criteria, you accept it or you don't. And so this is a little example of what that looks like. And eventually you end up with a solution. That you run this for a fixed amount of time. So I ran this for 10,000 iterations. And then this is what that looks like. So on the left, we have the initial route. This is just a randomly generated route through these randomly generated nodes. And this is the optimized route. And so you can see that the distance that it goes, or the distance of the route is much shorter for the optimized route, and therefore will take a lot less time. In these slides, the distance and the time are kind of unitless. They're generalized units. And so just keep in mind that simulated annealing will give you the reverse order of the route that you're looking for. So you can get either forward or backwards route, and trying it multiple times can give you a better answer depending on how difficult the problem is. And that's based on the fact that you're using you're using random numbers in it. And so you can get a better solution or not. The multiple traveling salesman problem is really similar. The big difference, and I really wanted to keep the simulated annealing because it made sense to me. And so I modified it to work with multiple traveling salesmen. And so you basically you just add the first node to the middle of your list of nodes. And then instead of taking two random indices throughout the entire list, you take a random index from the left and a random index from the right, and you swap the nodes at those indexes. And that way it's kind of like two salesmen bickering over where they're going to go, which houses they're going to hit, or, so that they just go back and forth. And at the end, you end up with a result that's the best for everyone. And so this is what that looks like. And you can see that the initial distance for this one might not have changed that much, but for the second one, it did a lot. And so ultimately, we cut down the time in half, which is awesome. And this is super useful if your drone has constraints, physical constraints like energy constraints, where you can run this for two drones and split the work. And so we did that. We did this kind of simulation for both. We did it with one UAV and then another with two UAVs. David, you mean?
This graph here shows the optimization with just using one UAV, and then in the next, this next image shows two routes, optimized two routes. So one thing to know is that for the most part, the best routes were those initial routes that we had along the road, which is significant which is still valuable for UAV because the UAV doesn't have to travel over traffic. However, also, we could have possibly produced better routes flying over the buildings. If we ran the RRT algorithm longer, it might have produced faster routes. Yeah, so thanks for watching. That's our project.